So this is 10.2 today, angles in standard position. I'm going to show you first of all how to draw an angle in standard position. So can you write Roman numeral 1, standard position? What does it mean for an angle to be in standard position? We typically, when we're drawing angles, we'll have an x and a y axis just as a point of reference. You really don't have to have it, okay? But I like to have it just as a point of reference. So I'm just going to lightly draw an x and a y axis here. And I want to show you what an angle in standard position would look like. Every angle in standard position has the same, what's called the initial ray. And the initial ray will always be on the positive x-axis. So right here, this is the initial ray. And then the more interesting ray, the terminal ray, depends on how big your angle is. Okay, so if I had an angle that I said was 120 degrees, it would be over here somewhere, about this. This guy right here is your terminal ray. Terminal. And that's the most interesting one, obviously, because every angle will have the same initial ray. The letter that we typically use for labeling angles is theta, which you used right last year in Math 2. Theta. Are you familiar with it? No. Okay, that's new. All right, so this is the letter we're typically going to use. It's an oval with a line through it like that, and what I'm saying is T-H-E-T-A. It's a Greek letter, theta. Okay, and it's just typically used for an angle. Sometimes x will be used, but usually with trig, they use theta. So this would be the angle, and we'd maybe call it theta, and one name for it is 120 degrees. There actually are a bunch of names for that angle. We're going to talk about that. Okay, typically your angles will fall where the terminal ray falls in a quadrant, but it could be that it falls right on what's called a quadrantal, or it is a quadrantal because it falls right on the line, the x and the y axis. Okay, so set this up here. Set up a light x and y axis, and then put your initial ray right here. So if that was my initial ray, and my terminal ray was right on top of it, and it didn't go anywhere, that would be 0 degrees. Okay. It also could have come all the way around, and I could do a directional arrow to show that. I don't want to do it right now because we're going to put a lot of other angles in here. But if I did a directional arrow that came all the way around to here, how many degrees would that be?
360.
360. Okay, so there's actually two names there for that. We could call it 0, we could call it 360. Okay, if this was my terminal ray, excuse me, my initial ray, and my terminal ray was straight up here, how many degrees would that be?
90.
90, so fill that in. And if this was my initial ray and then this ray over here was my terminal ray, how many degrees would that be? 180. Okay, and then straight down, where actually I came all the way around, started here and came all the way around to here, what would that be? 270. And then again, you can see we came all the way around and get 360 degrees. Okay, so the first part of today, you're going to be asked to just sketch and name the quadrant. Oh, let's name the quadrants. Review that. This is quadrant 1, and this is why we go in this counterclockwise manner, right? This one over here is 2. Quadrant 3 and quadrant 4 with Roman numerals. Anybody never seen the quadrants labeled that way before? That's
Yeah. Yes.
You've seen that before. Okay. All right, I would like for you then just to sketch and name the quadrant, and we'll just put the quadrant as we do it here. Okay, sketch. Let's do theta equals 200 degrees. Theta equals 200 degrees. Okay, so I'm going to set up just an x and a y axis just as a point of reference. On the positive x-axis, put your initial ray. And then you're really going to use those quadrantals. Again, these are called quadrantals. They're not in the quadrant. Okay, they're on the axes here. To figure out where 200 would be. Okay, so obviously you come around here, 180. You need to go a little bit more. It's going to be here in the third quadrant. Is it going to be closer to the 180 or closer to the 270? 180, right? Okay, so closer to the 180 here. And then what you're going to do is you're going to do your directional arrow, and you're going to say theta equals 200 degrees. And down here we're going to say it's in quadrant 3. And just circle it. Say it again. Yeah, that's coming up next. What if the angle, what do you suppose would happen if the angle was bigger than, say, 360? Like, what if I asked you to graph 370 degrees or sketch 370 degrees? What do you think that would do? It'd be the same as 10 degrees. And you know what? You'll show with your directional arrow, right? All the way around. So again, just as a point of reference, set up an X and a Y axis. Make your initial ray. Okay, so where will it be? Tell me what quadrant it'll be in. 1. And will it be closer to the 0 or to the 90?
0.
0. A lot closer to the 0. In fact, 10 degrees is hardly anything. It's really small. And the way you show the directional arrows, you should start on the initial ray. And because my pen's so thick, I'm going to come way out here, but you can do it in here if you can see it. But I'm going to come out here so you can see what I'm drawing. You start on the initial ray, and you come all the way around, cycle around, and then stop pointing at the terminal ray. And you show when it went all the way around, it's bigger than just 10 degrees.
And then so,
And while we're not doing this today, there's going to be something we're going to learn tomorrow called co-terminal angles. And 10 degrees and 370 are going to be co-terminal because they're going to have the same terminal ray. So there's a lot of ways we could name that ray right there, that same angle. Okay, what do you think happens if it's negative? What if I asked you to graph negative 120 degrees? What do you think that would do?
Go clockwise.
Yeah, it goes clockwise, the other direction. So setting up your X and your Y axis again. The initial side will still be right here on the positive X axis. But instead of going up first and counterclockwise, we'll go down. Now, where will it be? 120 degrees. Going to be in the third quadrant, closer to this, which would be negative 90, or closer to negative 180? Negative 90, yeah. Right here, if straight down was negative 90, this would be negative 120. Oops, I forgot to put the negative. Sorry, it should have been negative.
the 90's going to be on the bottom.
Well, negative 90. Yeah. So we actually could go back now. Let's go back to our quadrantals, and let's add these other names. 270 also could be called negative 90. And 180 could also be called negative. So, you know, I'm going to put a plus or minus. Just depends on which direction you're going, right?
Negative 180, right?
Positive 180 would have been to go counterclockwise. Negative 180 would be go clockwise. And I think of it from your initial. If you go up first, it's positive. If you go down first, it's negative. And what's another name for 90 degrees?
270.
Negative 270, right? So let's write that one in. Plus, we could go all the way around the circle, right? We could add 360 to those, subtract 360, a whole bunch of different names. That's going to be a future lesson. Okay, so this one is negative 120. Let's do one more negative angle. Where would negative 45 degrees be?
And so that would still be what quadrant?
Oh, yeah. What quadrant would this be? Quadrants don't change. This is still quadrant 3. That's good. Oh, and we didn't put this here. Can you come back up and put quadrant 1? Forgot the quadrants. Okay, now let's do negative 45 degrees. So let's set up our X and our Y axis as a point of reference. Put your initial side on the positive X axis. Okay, and then we're going to figure out if we're going negative 45 degrees, how far would that be? What quadrant would that put me in? 4. And where? Would you say closer to the 0 or closer to the negative 90? Right in the middle, right? It's right smack dab in the middle. Okay. And so there's the angle. Here's your directional arrow. And you'd say theta equals negative 45 degrees there. That's theta. Okay? Oh, quadrant 4. Good catch. Scale of 1 to 4. 1, I totally got this. Don't need to see any more. 4, I need to see another. Can you tell me where you're at, please, on this? Okay, I'm going to do another one that's bigger than 360. Should we do another one that's bigger than 360? Let's do theta equals 500 degrees. 500 degrees. Figure out where that would be.
I got it.
You got it?
Well, not right now.
Okay, so set up your X and your Y axis. Start your initial side, initial ray. How would you go about doing this? What do you think?
Subtract 360 from
Okay, subtract 360 because we know if we went around 360, then we're trying to figure out how much more. Okay, so what's 500 minus 360? What is it?
it. Or
140? Okay. So basically it's 360 plus another 140. Okay, so where would 140? Tell me what quadrant, first of all, would 140 be in? Quadrant 2. Okay, now this is 90, this is 180. What do you think 140 is closer to?
180.
A little bit closer to 180, pretty close to the middle. Do you know what's right in the middle is 135. So 140 is going to be pretty close to the middle, maybe a little bit closer to the 180. Okay, now how would we show that it was a full 500? Okay, so you're going to circle all the way around and then go all the way to the terminal ray. You always start that spiral on the positive x-axis, right? And then end on the terminal ray. And we'd say this is quadrant 2.
So we just subtract from 360.
Mm-hmm. Yeah, and it's even if we had a big negative one. Let's do a big negative one. Let's go theta is negative 600. Negative 600. We know we're going to go, down first, but I still would figure out, how much. If I went all the way around, that'd be negative 360, and then we're trying to figure out how much more that would be.
240.
240?
Yeah.
Okay. So because 600 minus 360 is 240. So here's our initial ray. And again, the idea is I'd go down, I'd go 360 all the way around, then I've got to go negative 240.
Maybe in
Quadrant 3 here. Because this would be negative 90, negative 180. We're trying to get another negative 240, you said? And actually,
It's in quadrant 2. Yeah.
quadrant 2, okay, think about it. This is negative 180. All the way to here was negative what?
270.
270. So what's 240 closer to?
270.
270. A little bit closer to 270. Not real close to 270, but a little bit closer. Okay, and then do that little spiral thing again, right? Start at the initial ray, spiral all the way around.
Does it matter what direction?
Yes, it does. You got to go down first because it's negative.
Oh.
Yeah. And we'd say that's quadrant 2. We just kept ending up in quadrant 2. They don't always, right? Okay, let's go to something called the reference angle. So we're going to be doing some more of this. There's a reference angle, and the name for it is theta prime. Again, I'm saying theta prime. That's how you read that, okay? Theta prime. And it's a reference angle. A reference angle, you guys, starts, it's an acute angle. Can you tell me what that is?
Smaller than 90.
Smaller than 90, okay, but not negative. Acute angles are between 0 and 90, okay? So not a negative angle. These will always be positive. So it's an acute angle made by the terminating ray, or the terminal ray, and the horizontal, or the x-axis. The horizontal axis or the x-axis. And again, we're going to call it theta prime, and it'll always be between 0 and 90. What I'd like to do is go back to the 6 graphs that we made and figure out what theta prime is in every case. Okay? So let's go to number 6 right here before that we did right here. As you can see by this terminal side here, there's 2 acute angles that are created. There's this one, and there's this one. Only one of them's the reference angle. Okay, and the key is it has to be made by the horizontal or the x-axis. Okay, so would you say it's the one below? I'm going to say this is below and this one's above. Which one's made with the x-axis? The one below, right? So this angle right here, this and this angle right here is theta prime. So would you put theta prime in there? Now we're going to try to figure out, wow, how big is that? And this was kind of a tough one to start with. That's okay. We can do it. How big was this angle? Well, when we came, we were doing 240, right? Negative 240 is what we were sketching.
Yep.
Isn't that what it was? So we came 180. How much more was this to make it 240? This was a really tough one to start with, but that's okay. How much more? So basically, what's the difference between 240 and 180? 60. That's your reference angle. Is that between 0 and 90? Yeah. This angle is 60 degrees. It looks about 60 degrees. Looks like we sketched that pretty good there. Okay, let's go up to this next one. Again, we're starting with tough ones. They won't always be this tough. Okay, again here, do you see that there's two acute angles? You got to get the right one. And you want the one that's made with the x-axis here. So this angle, this is theta prime. So put it in there, call it theta prime. We're going to try to figure out how big that is. We use 140, right? We use that. This from here to here was 140. So now the question is how much more to get to 180? And that would be 40. So notice when we're in quadrant 2, we're looking for how far is it from 180, right? Basically. Okay, let's go back to number 4 and find the reference angles there. Oh, number 4 is kind of cool.
45.
Yeah, Ava's already got it. It's 45. It has to be positive, but again, this is also going to be the reference angle, but now we're not doing a direction thing here. This is just, it's got to be between 0 and 90. That angle has to be 45 degrees. So theta prime is 45, whereas theta was negative 45 because that told us the direction, but the reference angle won't. Okay, let's go over to number 3. Do I want the angle that's above this line or the angle that's below it? Which one has the x-axis as one of its sides? The horizontal axis is one of its sides. The one above. Okay, I want this to be one of the sides. That means I want this angle right here. Yes?
So you always want the x-axis.
You always want the
The
x-axis.
one that touches
We
the
will.
x-axis.
Closest to the x-axis, you never will use the y-axis ever for a reference angle. Okay, so we're trying to figure out this angle right here. We went 120 to get here. How much more is left to get to, right? This would be 180, so how much is left? 60, that's your theta prime. Kind of getting the hang of the reference angles? Let's come to this one here, number 2. Okay, so here's my terminal ray. This is an acute angle, this is an acute angle. Which one's theta prime? The one above or the one below it? The one below. This one right here, right? I don't hardly have any room, so I'm going to draw an arrow in here. This is theta prime. Now, how did we get 370?
All 360.
360, and then we went how many more? 10. That's our theta prime, right? 10 degrees in this case. When you're in the first quadrant, it's a little easier to find. 10 degrees is your reference angle. You already got this one figured out? Can you see where it is? We want this side right here and this. This is our theta prime. How'd you get 20?
180. 200 minus.
Difference between 1 and 200.
200 and 180, yeah, because we came, this was too much. 200, right? How big was this? Well, we would take away 180. So if you took 200 and subtracted 180, you'll get 20. Okay, so theta prime is 20. How about our 120 degree one? Can we come back up here? Theta prime would be right here, right? Theta prime, how big is he? 60 degrees. Okay, once again, 1, totally got this, don't need another. 4, really could use another. Can you tell me where you're at? Okay, let's just do one more then. Let's do a new one. What do you feel like we haven't practiced very much? We did second quadrant quite a bit. Third quadrant, fourth, let's do a fourth quadrant one. Okay, can you give me an angle that's in the fourth quadrant that's positive?
Positive?
Yeah, give me a positive one.
355.
355?
Right about 342.
342. I like that. 342, that's a good one. Okay, 342. So set up our x and our y axis. Draw your initial ray. Okay, and we already said it was in the fourth quadrant. We made it that. 3/4 of the way around the circle, this guy down here is how many degrees? 270, and this is 360. So what's 342 closer to? 360, a little bit closer to 360, right? Okay, so I'm going to put it here. I'm going to draw my directional arrow.
Wait, would that be in the first?
342?
If it goes over 360, it'll go to the first.
Oh.
Right.
I wrote it down wrong.
Okay, so there's theta. Theta is with our directional arrow. You'll put it there. Okay, now, do you see there's two acute angles, right? You got the one below the line, you got the one above the line. Which one's theta prime? The one above it, right? Right here. It's got to have the x-axis with it. Okay, so theta prime. So the question is, how big is that? How would you find that? 360 minus 342. How much does that leave? 18 degrees, or theta prime is 18 degrees. Okay, listen, you guys, because the x-axis here, this is 180, and over here is 360, you'll always use 360 or 180 to figure out your reference angle. You won't ever use 90 or 270. Okay? What's that?
90 minus 42. Or, oh, wait, no, that's too much.
Yeah, if you wanted to find 42 first, you mean? Or
No, never mind.
it's not 42, that would be, what, 72?
Yeah.
72, you'd have to find that, and then subtract it. Okay, so you're going to have some reference angles there. One to four. What are you feeling? You want to see another one? Oh, okay, one's good. All right, we're going to go to then some more with the unit circle like we were talking about when we went over the homework. What you're going to do today is continue to find some coordinates. What is meant by a unit circle? It's a circle with a radius of 1. Okay? So a unit circle has a radius that equals 1. And there are some really, really cool applications of unit circles, because what will end up happening is you're going to see, we're going to discover is that the x-coordinate ends up being something and the y-coordinate ends up being something. And it actually makes it really easy to find these trig functions that we're dealing with this unit. Okay, so this unit circle, they're going to tell you it's a unit circle. Go ahead and set up a x and a y axis. And we're just going to say that this has a radius of 1. This is a unit circle where the r equals 1. And the directions are going to say find the coordinates. And then we're going to find the 3 trig functions based on these coordinates, okay? So all of these are going to be not in the first quadrant. So they're either going to be in the second, the third, or the fourth quadrant. So this first one I'm going to draw in the second quadrant. And this will be given, okay, you guys, they're going to draw this. So this right here would have been theta. And from here, what they're going to do is drop a straight down, perpendicular to the x-axis. And so what we just learned is that this little angle in here, you see what I'm pointing to, is theta prime. So I'm putting theta prime there, which you can't hardly see that prime, but if you can draw that a little better. What I've said there is that's theta prime. And then they're going to give you part of the coordinate, okay? So just like the problem that Sierra did up here, they're going to give you part of the coordinate. And I'm going to tell you that the x-coordinate is negative 15 over 17, and I'm not going to give you the y-coordinate, okay? So the first thing you're going to do is you're going to figure out the y-coordinate. I do believe that in the sketch they also tell you, but you should be able to deduce this, that this length right here is what?
1.
Yeah, because it's the radius, right? So you're going to put the 1 there. And then that negative 15 over 17, since it's in the x-coordinate, what that means is you came left 15 over 17. So this guy right here is 15 over 17, which I'm going to put as negative 15 over 17, which is fine. Okay, and what we're trying to find is this right here, which I'm going to call y. I'll call it the y-coordinate. Because the height, how far up you go, is the y-coordinate, right? Okay, what could we do to find it? Okay, she used the 30, 60, 90. But when you have a right triangle, what can you use? Pythagorean theorem. Okay, so how would it go?
Y squared plus negative 15 over 17 squared.
Y squared plus negative 15 over 17 quantity squared equals 1. And here's where it's going to end up. One thing that's nice about it is this will always be 1. Okay, so I need, the negative here is going to become positive, right? What's 15 squared?
225.
225. And what's 17 squared?
369.
That's 13 squared. Or 169. It's 13 squared.
It's
89?
289.
I'm guessing.
Yeah, it's 289. Okay, and then we're going to solve this for y squared by subtracting this over. Okay, so I'm going to kind of save a little bit of time here. What could I change 1 to so that I'll be able to subtract these two things? My common denominator would be 289, so I'd want to think of 1 as 289 over 289. Isn't that 1? I'm switching it to that on purpose, right? Got to be a little smarter here. Subtract the 225 over 289. Okay, so all I did was get a common denominator, just make the 1 here that, and I subtracted it. Okay, 289 minus 225? 64. Okay, now when we do the square rooting, we have to do plus or minus, and you should do that this first step here. It's plus or minus the square root of, so it'd be 8 over 17. This coordinate, you guys, is either positive 8 over 17 or it's negative 8 over 17. It's based on which way did we go. For the y value, if we went up, what should it be? It should be positive, right? This coordinate should be positive 8 over 17. Did you catch that? So you got to look at what quadrant it's in, and would the y value there be positive or negative? In the second quadrant, the y is positive. Okay, so that right there is the finding the coordinate. Then the next thing they're going to ask you to do is to find the sine, the cosine, and the tangent of theta. And you use, oops, you actually use the triangle with theta prime to solve it. And we're going to have much further discussion about why this is the case, but for right now you're just going to use this little triangle here, okay, where this guy right here was 8 over 17. You use the reference angle, okay? So sine, using SOHCAHTOA, was what over what? Opposite over hypotenuse. That's how we got the so. So from here, the opposite would be this y, which is 8 over 17, and what's the hypotenuse? 1. So 8 over 17 over 1 is just 8 over 17. Okay? Cosine, ka, is what? Adjacent over hypotenuse. So again, we're using theta prime. What's the adjacent side? Negative 15. Okay, and the hypotenuse is 1, which when I put that over 1, it would just be negative 15 over 17. Okay, this, you guys, is the beauty of the unit circle. The sine is just the y-coordinate. The cosine is just the x-coordinate. And as I said, tomorrow we're going to create a unit circle, and you're going to see a lot more applications of it, but that's the beauty of it, is because the hypotenuse is 1, the sine will just be the y-coordinate, and the cosine will be the x-coordinate. Okay, now to find the tangent, we would, what was that? It's TOA, right? Opposite over adjacent. This is going to take a little bit more work, but the opposite side for theta prime was, so we got to figure this out, 8 over 17 over negative 15 over 17. You got to keep the negative because it's in that quadrant. Okay, and then when we divide fractions, we can either flip the bottom over and multiply. That's what I'd do. Or we could clear the fractions. But let's just flip it over. So it'd be times negative 17 over 15. And the 17s cancel, right? Leaving what? Negative 8 over 15. And that's the tangent. Okay, let's do one more of these. Sketch circle, unit circle again. And let's put a point now down in the third quadrant. So I'm not going to draw theta in there because it messes it up a little bit here, but theta would have started from here and come all the way around. Okay? I'm going to draw straight up to the x-axis this triangle, and this will all be given on the homework. Theta prime's right here because it has the x-axis as one of its sides. You're going to be given part of the coordinate down here, and the part I'm going to give you in this case is the y-coordinate is negative 3/5.
the radius always going to be equal to 1?
The radius in a unit circle will always be equal to 1, so we'll put that in. This is always 1. Okay, now, the idea is one of these sides to where I drew the right angle, either this side or this side is -3/5. If it's in the y-coordinate position, would you say it's this guy on top or the one that's coming down the side there? Coming down the side. So this side right here is -3/5. We don't know the x, that's what we got to find. Okay? So again, Pythagorean theorem, right? So I'm going to set it up x squared plus -3/5 squared equals 1 squared, which is just 1. What would -3/5 squared be? 9/25. Okay, and then we're going to subtract the 9/25, and at the same time, let's switch 1 to 25/25, so we have a common denominator. 25 minus 9? 16. Okay, and then at this point, to get x, we're going to take the square root, and we got to go plus or minus, okay? Because theoretically, both of those answers are correct. And so we'd have plus or minus 4/5, but then we're going to look at the quadrant and figure out, would x here be positive or negative? And the question is, from the origin, which direction did we go? We went left, which is negative. Yeah. So this would be -4/5. Okay. Anybody see a shortcut on how we could have come up with that -4/5 faster? What do you know about? What do you know about those numbers? I'm talking specifically the 4/5 and the 3/5.
You add one.
Okay. Did that work here? This was 8/17 and 15/17. You know what I think of on those, you guys? I think of Pythagorean triples. 3, 4, 5, right? And this one, the 8, 15, 17 doesn't happen as much. But what's the other one? There's 3, 4, 5, and then there's multiples of it, right? What? I don't know why I put a comma there. 3, 4, 5, and then what's the one? There's another one that comes up a lot. 5, 12, 13. So that one comes up, and then this one here we had was an 8, 15, 17. If you recognize those Pythagorean triples and you see that, you know, you kind of have that and you got them in the right spot, you maybe could come up with that other coordinate without having to do Pythagorean theorem. But Pythagorean theorem only works. Okay, last part of this is now to find the sine, the cosine, and the tangent of theta. Okay? So the sine is the opposite over the hypotenuse. You're going to use theta prime. The opposite side is -3/5, and the hypotenuse is 1. -3/5. Okay? Cosine is the adjacent. What was our x-coordinate here?
-4/5.
-4/5 over 1. There it is. This is the cosine. This is the sine. Always. In a unit circle. And then tangent is opposite over adjacent. So we'd end up with -3/5 over
-4/5.
-4/5. And then you flip the denominator over and multiply. And what's your grand total? 3/4, right? Ends up being positive. Okay. And we're going to try to look for a shortcut for that too, but it's not maybe as easy for tangent. Okay, final thing we're going to do together. Open your packets and let's look at number 20. I just want to show you what they're asking you to do on 20. What's that? No, the air is supposed to be on. There was no heat on this morning. Okay, number 20. You got it? Aladdin, would you read the directions for us, please?
Fill in the missing sides for the special right triangles down below. Then find the acute angle of
Theta.
theta that satisfies the following equation.
Okay, so the first thing we're going to fill this in, and we're going to go ahead and do it if 30 degrees, the side opposite 30 degrees was 1. Okay? If it was 1, the side opposite the 60 degrees, which would be down here, should be what?
1.
Okay, 30 degrees goes A, A root 3, 2a. So 1 root 3 would just be root 3. And what would the hypotenuse be? 2. Okay? A root 3, 2a, where a is 1. On the 45 degree, I want this to be 1. What's the pattern for the 45 degree one? How does it go?
A, 2A.
A, not 2a, but a root 2. So this guy down here should be 1. And then this should be 1 root 2, which is root 2. Okay? They do it for the 60, but honestly, I don't want to do it for the 60. Let's just put the 60 right here. Okay? And we're going to do SOHCAHTOA with this. So they want you to figure out what theta is just by looking at the triangles, not using your calculator. Okay, by looking at the triangles. So what you're going to look at is which angle has a sine that's root 3 over 2, where sine is what over what?
Opposite over hypotenuse.
Opposite over hypotenuse, yes. So with SOHCAHTOA. So you want the opposite side to be root 3, and you want the hypotenuse to be 2.
60.
Okay? So the one that's opposite 60, I mean, where's the opposite side of 60? That's it. That's all you got to do is look at it and say, oh, theta is 60.
It's either 60 or 30. There's only, or 90. There's only 3 options, right?
Well, there's 30, 60, 90, or 45.
But I'm saying for number 20. Oh, you could do either. Oh.
Yeah, you could use either triangle.
Oh.
Okay, so here, cosine root 3 over 2. Cosine is what over what?
Adjacent.
Not a, okay, adjacent over hypotenuse. So we want the adjacent. Which angle has an adjacent side that's root 3? As you look at 30, oh, there's the adjacent. This would be, if I did the cosine of 30, I'd get root 3 over 2. That means theta must be 30. Do you follow?
No. Are we using the third triangle at all?
Well, it's the same as this.
Okay.
You can if you want, but it's the same as this. So I'd rather just do the one triangle. But okay, tangent is what over what? Opposite over adjacent. Now the idea is it needs to reduce to root 3. Honestly, I'd look at these and say, okay, which triangle am I probably dealing with? What's the only one that has a root 3 in it? Okay, 30, 60, 90. Now I'm trying to get the opposite side to be root 3 and the adjacent side to be what? Yeah, this is root 3 over 1. Okay, so which one has an opposite that's root 3? 60 has an opposite that's root 3. That's the angle then. That's the one you're picking. Okay, let's look at 23. What's the only triangle that has root 2?
45.
Okay, now you guys look. This has been rationalized. Do you remember what we said it was equal to? This is equal to 1 over root 2. If you unrationalize it, you'd get back to 1 over root 2. You could unrationalize it by doing the same thing, multiplying by root 2 over 2. Okay, sine is what over what?
Opposite over hypotenuse.
Opposite over hypotenuse. So we want to know which angle
45.
has an opposite side that's 1 and a hypotenuse that's... Does it matter which 45 I pick? No, same answer, right? Okay. Got it? So should we just do one more? 24. Tan is 1. Okay, tan is what over what?
Opposite over adjacent.
Opposite over adjacent. So I'm trying to get, this is 1 over 1. What kind of a triangle would have an opposite and adjacent side that are equal? 45. Yeah, and you know